Fakourfar from who did this work about stabilized annotations for mobile remote assistance with colleagues from the University of Calgary and University of New Brunswick.
Okay, good morning, everyone. I'm Omid from University of Calgary, and I'm going to present my master's thesis work, which has been a work in collaboration with University of New Brunswick. So maybe you have been in this situation before. Your car is broken down, and if you're like me, you have no idea how to fix it on your own. We all might refer to the owner's manual, or I would even try using YouTube's do-it-yourself videos. But the problem is we are often facing problems in which the solution is not clear, or we need constant guidance or feedback from an expert helper. So if I use the manual or a YouTube video, I won't have the right support, and I probably won't be able to fix my car on my own. But wait, we all have a good handyman friend from hometown who might be able to help. So the question is how? Well, we can set up a video call to ask for help. And we have mobile video conferencing that could allow us to communicate with each other. And we can choose between a variety of devices to make this communication happen. So your friend can use a tablet or any other handheld device, like a smartphone, to communicate with you. And if you need both hands to work on the task, you can use a head-mounted display, but they are not very common yet. Or some handheld devices like tablets or smartphones that are widely available, cheap, and it's easy to make applications for them. But wait, so I don't know what my friend is talking about, so this looks actually complicated. But we know from the previous work that being able to annotate the workspace by the helper person is critical in many scenarios. So the helper needs a way to reach into the scene and somehow annotate the workspace. So there are also lots of technologies in this area, like annotations which are atop the video feed versus those that are anchored to the objects in the scene. We call the first type non-stabilized annotations. So these annotations are drawn atop the video and actually move with the camera movement. So as you can see, when I move the camera, at this point they have lost their intended meaning. The second type of annotations are stabilized annotations, which are anchored to the objects on which they were drawn upon. So as you can see, when I move the camera, the annotations are still in their own place. And when I move the camera back again, I can still use them. But this type of annotation needs more effort and cost to be implemented. So it needs augmented reality tracking. It needs AR image targets like these that I have here. But as a driver, who has got any of these laying around in their car? So the question is, are they really worth the extra cost and effort? So as I said, there are commodity technologies that seem to support remote assistance scenarios. They are really cool and even popular among the users, but the question is, are they really worth the cost and effort? So it looks like they're actually not. So they are not the best option for all the scenarios. Instead, there are cheaper and easier approaches that seem to be just enough for many tasks, and they're easier to implement. So the bigger question is, how should we design effective annotation systems for mobile video conferencing with all these different devices and annotation types? Let me first show you these technologies again. So in terms of the device configuration for the worker, we have tablets that are cheaper and they provide more mobility for the worker person. And we have head-mounted displays that free both hands and they align the camera view with the eyes view. And in terms of the annotation systems, let's watch them again in action, but this time in the context of our study tasks. So we have non-stabilized annotations that, as you can see, are drawn atop the video and not anchored to any objects in the scene. and stabilized annotations that require augmented reality techniques to be implemented, but they are anchored to the objects in the workspace. So how should we choose a combination among these device configurations and annotation systems? So actually, prior work have already studied most of these, but there are two main problems when you read through them. The first is that they have not been very conclusive, and the more important one is that each study was run differently. By that I mean they have each chosen different task factors, and these task factors can lead different technologies to perform differently. And now I'm going to tell you about the task factors that we identified and used in our work. So we had locus of knowledge, whether all the knowledge for completing the task is located at the helper side or it's shared between the helper and the worker. We had movement and size of the workspace and the physical complexity of the task. So based on the history of research in this area, we were able to come up with 4 tasks, and we varied lots of task factors in all of them. So like if it's a 2D or 3D task, if it needs both hands, or it can be accomplished with just one hand. And these are our 4 tasks. So we had a tangram puzzle task, which is a construction task. It can be accomplished with just one hand, and it has a planar workspace. A graph task, which has a larger work area, the knowledge is shared, and it's again a planar. Sorry. Okay. There we go. It has a planar workspace, pretty much like the car repair task. An origami task, which needs both hands to work, and it's a 3D task. And a Lego repair task, in which the knowledge is again shared, and it needs both hands to work. So we try to address the problem with previous studies and consider all these task factors by designing and running 2 different user studies. In the first one, we compared stabilized annotations with non-stabilized and head-mounted displays with tablets. And in the second one, we studied another annotation system that we thought might be just enough for many tasks and compared them with non-stabilized annotations. So the first study. So in this one, we recruited 16 pairs of participants, and we designed a within subject study, and each pair went through all the 4 possible configurations. And this is how we set up our study. So the helper and worker were actually in the same room to get rid of the audio communication issues. But the helper used a tablet to communicate with the worker and to draw annotations. And the worker used a tablet for 2 tasks and a head-mounted display for the other 2. And our findings. So here are some quick charts about utility of stabilized annotations. So it turns out that stabilized annotations were no faster than non-stabilized version in terms of task completion time. That was interesting for us, but they were actually preferred by the users. So we don't have a good reason for that, but we just think that might be an effect of novelty. And here is another important finding that we had from observing our participants doing the tasks. So annotating video is really hard. I'm going to show you a video that will show you a problem that we saw several times with different groups. In this video, you will see the helper trying to draw an annotation on the video, but at the same time, the worker is moving around the object, which is an origami paper. And this frustrates the helper. Let's watch the video, and I'm going to get back to this point later on.
So basically, you want to like fold. I'm going to draw on this, okay? Okay. So stay still. Fold like that. Like you just move it like a square.
But fold the whole thing.
Okay, don't move the paper. Okay. Okay.
So maybe the most interesting finding was this one. So we were able to classify the annotations into 3 main categories: reference, procedural, and pointers. So the first type was reference annotations that were needed to be referred later on. like end states or legends. So in this video, you can see the tangram puzzle task. The helper draws the outline of the final shape, and then the worker works on his own to do the task. Then we had the procedural annotations that show some kind of process, like folding or rotating objects. And this is one from the origami task. And we had pointer annotations that were used to temporarily point towards objects in the scene. So this one is from the Lego repair task. And this is the distribution of all these types of annotations across the tasks. So as you can see, a large portion of annotations are either procedural or pointers, about 61%, which means they are needed only for a short amount of time, maybe a few seconds. So to summarize, stabilized annotations were preferred without having any actual time benefit. And after classifying the annotations, we found out that most annotations are ephemeral. And annotating video is hard regardless of whether the annotations are stabilized or non-stabilized. But if annotating video is hard, now you can guess that annotating pictures is easy. So as I told you before, most of the annotations are ephemeral. So what if we could make temporal annotations, but not on live video, but on still frames, on pictures? So we call such technique temporally stabilized annotations. So I'm going to show you a video. So here the helper starts drawing the annotations, the screen freezes, and it keeps frozen for 2 seconds, and after 2 seconds, it just continues the video feed. This technique is also easier to implement than the stabilized version. So this led us to this question for another study on another annotation system. We called it F2 or freeze frame. And that is, does the simple freeze frame approach for annotating provide any benefit over annotating the live video? So for this study, we recruited 6 pairs of participants. They only used a tablet, both the helper and the worker. And we used the same Lego and origami task. And again, we had a within subject study. So in one sentence, it worked pretty well. The good thing was that now the helper could draw on a still frame, a picture, instead of live video, so it was much easier for them. But those few seconds of freezing the frame caused some loss of context for the helper, because they had no clue what's going on the other side. So as you can see in this video, the helper starts drawing the annotation to the right. The screen is frozen, but after that, the worker has already rotated the structure. So let's talk about the pros and cons of this technique. First of all, since we are annotating on still frames, it's much easier, and we won't have the problem with moving camera or objects. It's also easier to implement because it does not any sort of augmented reality technologies. But you saw the loss of context problem, which can hinder real-time feedback. But we think this problem is easily addressed. We can provide another live view for the helper as he is drawing the annotations at the corner of the screen. So temporal annotations are a very easy technique that can support most remote assistance scenarios. And this is what we're going to do in our future work. So to summarize, we identified 3 types of annotations, of which the procedural and pointer annotations are only needed for a short time. And most tasks can actually be accomplished with these ephemeral annotations. So we looked into annotating pictures instead of live video, and they were actually a win. So that's our takeaway from this paper, and thank you.
All right, we have time for some questions. You can line up at the microphone for any questions. In the meantime, I'll ask you one. I was curious, can you imagine what kind of scenarios would these mobile annotations be useful compared to using self-help videos on YouTube, which I think a lot of people use right now to help themselves fix a car?
That's a good question. So we think they're used mainly for tasks that need some constant guidance or feedback from the helper. So like the car repair task, it might not be too risky, but there are maybe more riskier tasks like repairing a jet engine or something, that they actually need constant feedback to just don't do something wrong. And then that's why you need to just refer to objects and point at things. So that's when it's needed.
Arnold Chalmers, University of Illinois, Chicago. In a temporal stabilization model, do you freeze the video on both ends, or is it just the helper's video that's being frozen?
It's on both ends.
Okay.
Yeah.
Thanks.
Yeah.
Any other questions?
Yep.
Did you consider fading the annotations instead of freezing the video?
What do you mean by fading?
Like they appear and then after 2 seconds they gradually fade out.
So that's a good approach. So it's basically now both freezing and fading, so it fades after the 2 seconds. But what we needed to do was to have some sort of a stabilization. So we get to that stabilization with that freezing the frame, but with just fading, so you don't have the annotations there for any amount of time. So you can't stabilize them in somewhere. Yeah.
I was just curious if the frame was frozen for a fixed amount of time, for like 2 seconds, or as long as it took to annotate the frame.
So it was fixed. So when you actually draw the annotations and you put your finger up, then you had 2 seconds for the annotations to be there, and then it was unfrozen. So it was exactly 2 seconds. Yeah.
If you let it fade away, you
Mhm.
could give the user the opportunity by just clicking to let it stay for another while. Wouldn't that be an option?
That's right. So that's what some prior works have worked on. So you give the control of whether you want the annotations to be there for a few seconds or you want to automatically fade them or unfroze them. So there are some approaches on this, but one of them is absolutely that you have the control on where to fade them or have them on the screen. Yeah. Cool. Thank you.